All right, so I want to finish that introduction to distributed systems. This should give you a very fast overview of what kind of things we want, what kind of problems we want to solve. That's the biggest question in any area, right? And what I'm going to try to do is try to point out the obsessions that distributed systems will have. I mean, why do I call them obsessions? So at least this is the way I'm thinking about things. Every area, computer science or other kind of sciences, is obsessed about certain topics. In order to think like them, you have to switch, at least temporarily, to the same kind of obsessions. So they have a deep regard for certain things and a deep disregard for others. And this is exactly how you understand the specific area. So for example, in how many people here take algorithms, the algorithms class? Right? All of you have to, right? You know, it's unavoidable. OK. So what's the obsession in algorithms? The big O notation, and in particular, the chasing of logarithms, right? To the point that they prove certain things are better than logarithms, right? Log star. Union bound is log star, which is impossible to tell apart from O of 1, but it's a fancy way to say a little worse. But that doesn't mean necessarily that in practice the program runs faster or doesn't run faster. It's just a particular kind of obsession in that area. So the important thing here is going to be what are the obsessions in distributed systems? What are the things distributed systems like to talk about? And I'll try to explain why. Okay? All right, so one of them is this transparency deal, right? Make as many things as possible transparent. And as I mentioned 3 lectures back, this obsession has even been standardized, right? There is an ISO standard of how exactly should you talk about the transparency obsession. I'm not going to go through that again. Another one is the scalability. It's the central, if you want, idea in distributed systems. Any centrality in the algorithm, it's evil. Let's get rid of it. None of the things that we do should be centralized in any way, shape, or form. And then this is the standard reasons why, I mean, this is the standard things that are going to happen if you standardize, if you centralize, and they're all considered bad things, right? So centralized services means a single server for all users. What if that single server goes down? Let's put more servers. Centralized data, a single online telephone book. This is similar to the centralized services. Centralized data might actually mean data it's on a farm, available from multiple websites, but is still owned by a single, let's say, entity. And that could be also a problem for different reasons. Centralized algorithms, right? Doing routing based on complete information. This is a much bigger kind of evil. Decentralized algorithms are really the core of distributed systems. Can you design algorithms that don't have complete knowledge? We're going to come back to this later. Now, what I want you to understand, though, okay, and I have to be honest with you from the beginning, what I want you to understand is it's good to be obsessed, don't get me wrong, but at some point it comes back and haunts you. Being overly obsessed about things is not healthy either, right? Under certain circumstances, it might be perfectly acceptable to design centralized algorithms. For example, if the total amount of knowledge that's required is relatively small, you're better off by telling everybody that knowledge and let them run whatever centralized algorithm they want. Also, centralized services. If you have 100 customers, you really don't care about decentralized services. You don't. So if you're sure that you're only going to have 100 customers, do the centralized solution, move on, and do something else. There's no need to design a super scalable solution if you're not sure that the quantity, quality demands of the users are going to get to the level where that's warranted, right? So treat them exactly like obsessions that you can turn on or off, okay? Now, of course, the interesting question in this class is going to be, if I do want to achieve these goals, which are important goals under certain circumstances, what do I do then, right? But you don't necessarily always want to do that. And I'm going to argue throughout the class that solutions already in existence try to knock off some of these obsessions because engineers said, hey, it's ridiculous to do this, let's not do it, right? So a lot of, for example, the systems and Hadoop is like this, right? A MapReduce engine, in fact, has quite a lot of centralization, right? Which immediately makes it a not good solution in the eyes of the distributed systems community. And hey, let's improve it. And you have thousands of papers that talk about how you could remove that centralization requirement in Hadoop. But of course, nobody bothers to run any of those in practice, and they still run, and they're happy about an actual reasonably centralized, at least decision maker in Hadoop. Okay? All right, so these are the so-called scalability problems. I mean, what's scalability first? We're going to talk about scalability up and down. You already have used the word scalability, I'm sure, but it's important to say what's scalability, okay? And this is an obsession that's good, but not as a single obsession, okay? So scalability refers to the fact that if I add more hardware to the problem, ideally, if I double, let's forget about hardware, because I even hate things like if I double the number of processors, something else, I mean, the performance doubles. What I like to think in general, and I think this is the only reasonable obsession, is to obsess about money, because it's the scarcity of all resources. And I mean, replace money with anything that costs money and is the same, right? Gold or whatever you want, okay? So the question to me, to a large extent, and this is the ultimate scalability, is I have problems because the system is too slow. I would like to improve the speed of the system by a factor of 2. Can I just throw the same amount of money as I already have invested in the system and get an addition to the system that allows me now to run twice as fast? If yes, I achieved at least money scalability, but there are many other kinds of scalability. But it's always about, if I put more resources in, is the running time going down, number of users go proportionally up, and it's always that trace of the proportionality. Ideal scalability, it's always thought of as proportional increase in resources, proportional increase in how good the result is. And you're going to see lots and lots and lots of papers in which they say, hey, I designed an algorithm. My algorithm is scalable. How do I prove this? Well, let's put on the x-axis the number of cores used to run the computation. On the y-axis, the running time, or whatever, the throughput. And then you show linear increase. When you have more cores, things get linearly better. Then you draw with a dotted line the ideal curve, right? So this is how a good distributed systems paper looks like. You say, let's say throughput, how many requests I can do per second. You say, ideal scale up. My scale up. You see, I'm very, very close. It's so good. What's a not so good scale up? We've seen some pictures like this. It goes like this and then flat. This is the number of cores, let's say. Right? Not good, good. Scalable, not scalable, or so they say. Now, again, having this, it's a good thing. But it's not a solution for everything. I want you to understand this throughout the class. And this is my biggest problem with a lot of the distributed systems. They are scalable, but they're not particularly efficient in the first place. So imagine that I'm not going to only show you the scalability. I'll show you that a system, that a single system can deal with 10 million users, has no scalability whatsoever, but can deal with 10 million users, versus your scalable system that can deal per system with only 1 million, with only 100,000 users. You literally need 100 machines, even if your system is scalable, to get to the point of where you compare to my machine, and you might never grow beyond those 10 million people. So scalability is not everything, and that I want you to keep in mind from the beginning. And now, of course, if you have a highly efficient algorithm that's also scalable, hey, that's fantastic, okay? So things about scalability, I mean, there are many obstacles to achieve scalability. We're going to see this. These are some of the reasons. No machine has complete information about the system state. When you look at the system as a whole, and we're going to do this, you draw a nice graph. And you say, this machine does this, 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 they exchange this, whatever they do. The trouble is, nobody can see that graph, right? So think about, for example, all the computers and the routers and whatnot in the internet. By the way, you can buy programs that cost hundreds of thousands to millions of dollars to just draw the topology that might exist at some point in some corner of the internet, right? You might know the machines you control, but you don't know the machines somebody else controls, and the internet is made out of this many, many, many parts. And knowing how parts come together might allow you to optimize the network, but there are no good tools to just give you that global picture. So global picture is very hard to achieve. Any algorithm that depends on that is going to be in trouble, right? Machines make decisions based only on local information. Now, you can make decisions based on non-local information, but you have to exchange information with other entities. And what's the problem with that? That takes time. By the time the answer comes back, the state of the system changed already, right? So if you have a very dynamic environment, and that happens, for example, with these mobile devices, right? For example, imagine that you would like to say which students are in campus, and you're just watching the MAC addresses on their phone. By the way, this is kind of possible now. It's scary, possible to some extent. But in order to have a very good idea where everybody is, you have to move fast enough with the messages and what you track, because otherwise the people already moved, right? And if people are on a train, you're in deep trouble because the train already moves very fast, right? failure of one machine does not ruin the algorithm. This is, you remember the transparency? One of the transparencies was failure transparency. Hide any kind of failure and make it look as if nothing happened. If you do that, that's great for the user, right? But this is going to be one of the very hard things to deal with. How do you mask these failures? How do you make sure that one machine there does not ruin the rest of the algorithm? That essentially is going to mean that you need to build some redundancies in the system. Actually, a lot of redundancies in the system. Okay? So we're going to come back to all of these things as we talk about distributed systems algorithms. No implicit assumption about global clock. Now, this is a weird one. Okay? This is a really, really weird one. What exactly does it mean that we don't have a global clock? We all have watches, right? There is an official time. What does it mean not to have a global clock? Okay? But here's the problem. The problem is we need an extremely precise global clock, right? So when you're doing operations on a computer, they happen at gigahertz, right? Especially if you get that nice close to assembly code. So everything is measured in nanoseconds, right? So it would be fantastic if we have coordinated clocks with the precision of a nanosecond, right? If that would happen, then a lot of good stuff, it's going to work in our distributed algorithms, because any activity we do, we can just put a timestamp of when it happened, and we would have a clear idea of who was first. Somebody asked in class, yeah, but what if this guy sends the message first and this guy receives it second or whatever? How do we even know what first and second means? Why is this important? I'm going to talk extensively about this. It's extremely hard to get highly coordinated clocks. Now, how many people here have heard about the GPS? Well, you have it on your phone. You better have heard about it. In principle, how does the GPS work? Good. So that's very nice, right? We put satellites. So what? Well, so here's a trick with GPS. The little GPS, your phone, it's in fact solving a trigonometric problem all the time. It's a spatial 3D trigonometric problem. What it's doing is it listens to signals coming from satellites. Those signals contain in them the time at which the signal was produced. It takes a while for the signal to propagate, right? So if you get a signal from 4 of those satellites, you can actually compute how long it took the light to go from the satellite to you. You know where the position of the satellite is because that's encoded in IDs in these messages. You can solve that trigonometric problem and say, this is my 3D position on Earth. So that sounds fantastic, except that it requires a magic ingredient. The magic ingredient is the clocks on all the satellites have to be coordinated at the nanosecond resolution, right? So those satellites so by the way, the precision of the GPS increased significantly even in the last few years. I mean, the coolest thing I've heard is people that have tractors, farms, right? They now can guide the tractor via satellite. It apparently costs about $1,500 to sign up for that special GPS program because the resolution of that is 1 inch. They can tell the position of the truck with the precision 1 inch, which means they can guide that big tool, that harvest or whatever, very precisely not to miss anything, because otherwise it's an extremely boring job. And they have these fancy algorithms. This is the best way to design algorithms, right? Design a nice algorithm that can go on a weirdly shaped field so that in the shortest amount of time you pick up all the whatever you're supposed to pick up. But you need that 1 inch resolution on the GPS, right? By the way, the GPS that I have in my car, sometimes I wonder if it even hits the right town, right, let alone an inch. So how do you get such a small resolution? Well, the secret is not in better ways to compute something. The secret is really in better coordinated clocks, right? By the way, all of those satellites have extremely expensive clocks. They are atomic clocks, cesium-based atomic clocks. And this is the kind of technological problem that had to be solved on the satellites. Now, is it possible to achieve extremely coordinated clocks? Yes, but it's extremely expensive. You're not going to see one in your phone anytime soon, right? Now, you're going to see a lot of algorithms depend on some sort of a clock there. And the clocks make it much, much easier, much simpler. But we can't put a multi-million-dollar cesium clock that's yay big in every phone, right, to get those clocks. So you might as well just give up and say, I can't coordinate clocks. It's so bad, actually, that different cores in a single chip don't run on the same clock. Literally. They all have their own clock, their own beating, and they cannot tell if two things happened at the same time. And what does it even mean for two things to happen at the same time? Because any information about that thing happening takes at least the speed of light to propagate in the other place, right? So things are really messed up when it comes to the same time, okay? Oh, by the way, this is the coolest thing ever. With the GPS, it turns out that the precision of the GPS would be only about 2 miles as opposed to this kind of inches if you would not do a relativistic correction. So you have to use the Einstein's general relativity to account for the fact that the time goes a little bit slower where the satellites are because of the gravity. The gravity is a little bit smaller there, and this is probably you haven't bumped into this, right? Einstein wrote some very nice, very fancy equations to describe how gravitational fields influence the time. It's completely messed up and upside down. I mean, you have to know so much to just implement this kind of a GPS, okay? And yeah, no cell phone cesium clocks anytime soon, for sure, okay? All right, now, when it comes to scalability, there are many more traditional and less traditional techniques we are gonna see in the class. And these techniques become very, very important, right? Let me give you just one idea. And this is something that you're almost guaranteed to bump into, right? So the model that's everywhere now is you have front ends that are either, for example, applications in cell phones or web interfaces for a computer or whatnot, and some sort of backend, some sort of a combination database and web servers and whatnot in the backend. And one of the big questions is, how can you design such a system that can support millions of users? We're going to talk a little bit about later, a little bit about Instagram. How many people heard about Instagram? These guys with click pictures, forget about them, just put them there, okay? The trouble Instagram ran into is they went from 50,000 users to 1 million users in a week. They panicked, okay? They were just basically some kids that took some off-the-shelf tools to design this. It was going fine at 50,000 users. And the system started to crawl the moment they reached 1 million. And it was going up because it just exploded. Now, why it exploded in terms of popularity, I don't know. They've done something right. But the problem is it exploded. So they had to redesign the backend completely, rewrite completely the backend. And they've done it in 3 days. Okay? I call that the scalability wall. A lot of startups die because they cannot go through the scalability wall. The initial solution they designed is not going to allow them to take those millions of users, right? You don't solve that problem, your app dies. That's it. I mean, the moment it becomes sluggish, nobody uses it. Nobody's going to have patience. People with cell phones have absolutely no patience, right? Absolutely no patience. You have exactly 30 seconds to convince me this app is worth anything. If not, delete, move on to the next one, right? I'm the same, by the way. All right? So some of the scaling techniques are move computation away, move things away from the server, and this is one of them. Now, this is something that people usually don't talk too much about. Traditional way is, for example, this is web forms, right? Fill in information in a web page and then send it to the backend, and then the backend computes all of that. I mean, first of all, you send a lot of information, does analysis and says, hey, this form is good, not good, send a message back, and if it's good, maybe do whatever the form was supposed to tell you to do, a transaction in a database or things of this sort, okay? Now, what's the problem with this? The server does too much, right? Now, I mentioned this before, JavaScript, right? It's now at an amazing level. By the way, even phones run it well, let alone desktops. I've seen Unreal Tournament. How many people know about Unreal Tournament? Come on, it's not a shame, okay? Unreal Tournament is this, well, somewhat violent but very 3D game. It has been ported to the web browser. This is because of a very, very nice tool that can take C++ code and generate a very specific kind of JavaScript code. But the point is, JavaScript runs so well in the browser now you can run 3D games, right? Now, in my opinion, this is a tremendous opportunity. Why? Because if you can run 3D games, you can do so much more in JavaScript, which means you should move a lot of stuff in the front end, in the browser. All the validation for the forms and whatnot, especially the really stupid mistakes, right? And now, you cannot prevent in this way attacks, because then they're going to replace your JavaScript code and do low-level codes. But at least things to help the user, you can definitely delegate them to the front end. That immediately means you're more scalable in the back end because the server does less. The server just providing some data is not doing this crazy other computation that's needed. This is extremely important, for example, for visualization, in which all the computation to run the visualization is run in the JavaScript, in the front end, and the server just says, here's the data. And then you can support thousands, millions of users, no problem. You just need bandwidth. And then there are standard tricks like compression and other things to make it even more scalable. Or if not, you move to another data center or whatever. Right? All right. So many, many techniques for this. Another one, for example, and this is a more geographical scalability. The trouble is light and electrical signals in general. They need a lot of time to go from one end to the other at the scale of these very fast messages. Right? So that already puts a lot of constraints in how fast you can talk. So how do you solve latency problems? So scalability can be in terms of many aspects. One of them is latency. Right? Humans tolerate about 300 millisecond total latency. Anything above that is very annoying. And I'm sure you yourself have been annoyed. Right? The web page loads very slowly. Or you try to do something in an app, and it seems to kind of grind in there. You have bad things to say about the web designers, right? It's the back end, for sure, right? So how do you solve these things, especially in a geographical way? Well, for example, if you could tell from what country people come, assuming that the network layout kind of goes with the country, which is not necessarily true, then you can, in fact, position multiple servers for your service in various countries or at various ISPs, intercept then the request that normally would have went to your main website that's maybe in US and try to serve it from that closer server. By the way, I mean, this sounds like a cool thing to do, right? Has been done. Akamai. How many people heard about Akamai? What, few of you. Why the rest of the people did not heard about Akamai? Because they don't care to normal users. They have as a customer the big guys you know about. Right? Google and Facebook and CNN and whatnot. So what do? It's called a web accelerator. Instead of you going all the way to the end of the world to talk to the CNN web server that might be, I don't know where their servers are, they put a very nice server at your ISP. They propagate the content that CNN wants to have, and maybe it's delayed by a few seconds, but nobody's going to notice. And then when you go to CNN.com, it gets intercepted by your ISP and runs on that little server. So Akamai pays for hosting servers at the ISP side, and this is why certain websites are so fast, right? Because of Akamai, because of this scalability through geographical techniques in which you don't only have multiple servers to take the load, but they are much closer to you in terms of time to access, right? Now, an extreme version of this, by the way, is millisecond trading. How many people know about millisecond trading? This is about making money very fast or losing money very fast. So what's millisecond trading? Means I want to buy and sell stock or other things that have money associated with them fast, at a millisecond level, right? Now here's the problem. A server in Japan, right, or even in Gainesville might be 100 milliseconds away from the New York Stock Exchange's very fast trading server. In the time it takes the message that says stocks of Microsoft have been sold at this price point, in the time it takes to make it to my server, let alone the time it takes me to process it and so on, the guys that have the servers in Manhattan, right, where the servers of the New York Stock Exchange are, got the message, already decided to buy or to sell, what to do, and send a buy or sell request, and they already have the order fulfilled by the time the initial message gets to me, right? Now, why is that important? Because you can make a lot of money by just riding small fluctuations, right? So you see, people try to predict the stock market for the longest time, and these guys say, hey, you don't need to predict the stock market. You only have to predict what's going to happen in the next 100 milliseconds. If it takes time for other people to react, right, if they see the market going up, if it takes them 300 milliseconds to see that it's going up, if I can trade 10 times faster than the 300 milliseconds, I'll make money. And you're making money by riding this wave. You see it going up, you start buying. You see it going down, you start selling, and do it faster than anybody else. Now, question. You want to do millisecond trading. Where should you have your servers? So here's what's happening. You cannot have it at the stock exchange, but you can have it across the street from the stock exchange. So the most expensive real estate in New York, it's across the street from New York Stock Exchange. It's a building. that has a big fiber going to that building, right, where you can place your millisecond trading servers. And that's where 99+% of all the millisecond trading servers are. And people are paying thousands of dollars rent for a couple of square feet per month, right? So it's an extreme version of scalability. You scale in terms of distance, because if you don't do so, what's the point of trading if those guys are riding the wave and you're not, right? By the way, I've heard the coolest thing also. But what I'm trying to do in this class is to explain to you that everything that happens here, it's connected with everything because of cell phones and websites and whatnot, right? So a lot of these stories have an interesting meaning that I'm hoping you're going to remember mostly because of the story, okay? So the thing that I've heard about is that they are building now a transoceanic fiber to go from London to Japan, to Tokyo. And the expense of that is very, very large. I mean, why would you do that? Because you already have ways to get to Japan. Well, they're going to do that because they can cut down the travel time of the messages to 100 milliseconds versus about 300 milliseconds. And the business model for that fiber is very simple. We are going to rent bandwidth on the fiber for people that want now to trade in between two stock exchanges, the London Stock Exchange and the Tokyo Stock Exchange. So essentially, if you don't rent bandwidth on that fiber, you might as well not bother to do arbitrage or some other kind of trading in between the two stock exchanges, right? So by the way, enormous fortunes were made by just realizing that there is a little discrepancy in price between things and trading fast to fill the gap. Right? So if you know 300 milliseconds, 100 milliseconds before anybody else, that the price of the same commodity is a little bit higher in one stock exchange than another, right? By doing many, many transactions or large volume transactions, whatever, you can make a lot of money. And people made a lot of money, right? So this is probably the most direct way in which concepts of distributed systems correlate with raw, large amounts of money, right? So a particularly lucrative application of what we are going to learn in this class potentially is to start doing those millisecond tradings. By the way, don't play with your own money. You're going to lose all of it very fast, okay? And you can still lose billions of dollars within 1 second. Okay? That happened, right? One of those algorithms. So think about algorithms not running properly. When one of the fast trading algorithms runs amok, in few seconds before anybody can press the red button and shut down the system, you already lost $1 billion, and that happened. I think JP Morgan lost a couple of $1 billion because one of the fast trading algorithms ran amok. Not to mention that destabilized the market a couple of times, and the whole market went haywire, and they had to stop trading on the New York Stock Exchange because some of these algorithms decided to do things, right? That's probably the way, as a computer scientist, that you can create the most havoc, right? You convince people to let you play with these dangerous things, and then you do things, okay? All right. Pitfalls, these are the classic pitfalls associated with developing distributed systems. So what pitfalls means in this context is things you might assume are true, but in fact they are not. And if you depend in a crucial way on them, then you're in trouble. Again, maybe you are actually, or maybe you're not, right? So at some point you have to draw a line and say enough, it's enough, right? So it's this common sense that's kind of hard to get, because if you get overly obsessed either about the pitfalls or scalabilities or whatever, you're going to design these non-existing solutions, or you never design a solution because you convince yourself that it's not worth designing a solution because you cannot get that completely decentralized algorithm, right? But you can write papers about why that's not possible, maybe. We're going to see negative results in this class. So it's interesting, actually. Okay. So let me go through them, and then I'll come back a little bit to the negative results. So pitfalls, right? Network is reliable. Well, it's not, unless it's a local network. Anybody has any idea how reliable a wired network is? You see, so this is the problem. There are pitfalls to pitfalls. If you really have your data in a rack, so just a nice support for the machines, and you use high-quality network cards, the reliability, it's incredible. It's really stupid to assume that your network is not reliable, literally. Okay? But if you're talking about wireless network, not particularly reliable. You're talking about very long-distance communication through many hops, not reliable. So even this network is reliable can be bent, right? By the way, the reliability right now for wired networks, I think, is 1 in 10 to the 18 bits gets flipped or something like that. I mean, you're not going to see a bit flipped in a year, basically, on a reliable network, local network. But you're going to see a lot of bits messed up in wireless networks. The network is secure. We are going to talk a little bit about security, and this is one of the biggest problems right now. There's no such thing as secure, right? So you probably already took or have seen some security in some other classes, right? So it's always insecure in particular. In some ways, cryptography helps a little bit. We're going to touch on this later. The network is homogeneous. That essentially means that everybody who participates in the network has roughly the same characteristics. It's absolutely not true. I mean, even for the cell phone, some people simply have a very old cell phone. You have to cater to them as well. Or to say, well, unless you run whatever, the Samsung Galaxy 4, I'm not going to let you go on this website. That's not a particularly good business model, right? Topology does not change. This is, again, not true for many, many, many reasons, especially once you achieve a certain size. So what's happening is, if things are relatively small, these pitfalls might not be quite as big as a pitfall. But beyond a certain size, right, things are going to start going down, sometimes exponentially. I'm going to talk about this when we talk about sensor networks. Okay? I happen to do some research on that, so I know a little bit more than the textbook writers on the issue. But all right, latency is 0, never is 0, even when two cores talk to each other. Okay? Bandwidth, it's infinite. Definitely not true. You try to squeeze too much on that pipe, it's not going to be good. And it can get bad in much weirder ways than you reach capacity and you cannot send more. Transport cost is 0. There is only one administrator. This has to do more with how do you keep up a large number of machines, right? So the large data centers now can easily host 100,000 or more machines. Even if you're just Google and you try to be very organized, you still need multiple admins to take care of so many machines to do things, right? So that assumption might not be true. All right. Now, one of the more direct ways to put together a distributed system, and this was actually explored quite a lot, is to have some sort of cluster computing system in which you have multiple independent machines, you have a network connection in between them, and some sort of a software, middleware of some sort, to do some coordinated task. Now, we are used to coordinated tasks because that's how we interact with other human beings, right? We normally, normally I would say we don't, but I'm going to mention this, like we normally don't control each other's brains, except that some guys from, I don't remember, not Carnegie Mellon, one of the universities managed to get a brain-to-brain interface. A guy was thinking about something and got another guy to move something on the screen. It's somewhere on YouTube or whatever, right? So the brain-to-brain interfaces are coming, but for now, we are just doing some sort of, we communicate one way or another, and we do something. The same thing has to be done with computers, and this is really what the distributed systems is all about. So one classic way to set this up is to have some sort of a master node that coordinates all the activities and then a number of worker nodes, except that this breaks one of those obsessions, right, which is the centralization. Part of the algorithm is centralized. We have only one boss, right? So if the boss dies, the whole cluster is unusable. Unless, and we're going to see this in class, we designate somebody else to be the boss and it takes over to being a boss, right? So that's, for example, called leader election. So one fancy thing that distributed systems people looked at is, hey, how could you design a system in which if the boss dies, so we can have a boss, that's not a problem, and that actually makes the algorithm faster, but if the boss dies, we elect another boss and that guy takes over and we switch over to another version of the algorithm and we are fine, right? If you do that, then you have a very hard to kill network. You literally have to disrupt a lot more things than just kill the boss, right? What happens if a compute node goes down, for example? Well, if the boss knows what the compute node was doing, it could delegate exactly the same work to another worker. But that assumes that the data is then available on another node, so you need some redundancy in the data to be able to do these things. These are the kind of techniques used in distributed systems to design such systems that are going to be resilient one way or another to particular kind of faults. Okay? The trouble is when the master node is not dead, but it's a little bit hiccupy, right? Or a little bit more than hiccupy, right? Then it's a problem because you might say, hey, let's assume that that guy is dead. You bring another master, and then suddenly that guy wakes up and you have two masters, and you can wreak havoc in your algorithm when you get contradictory information from now two master nodes. it's doable. Things can be done, right? But that's what distributed systems, these are some of the core issues in distributed systems. Now, grid computing system, I don't want to talk much about this. This was extremely hyped up for a number of years, and now it's dying down because other buzzwords came up. By the way, there is no area in computer science that has more buzzwords than distributed systems. Right? Maybe databases. Okay? But in between these two, you have the most buzzwords. So, for example, who here knows what cloud computing is? What's cloud computing? Well, let me tell you a secret. Big companies were asked specifically to define what they mean by cloud computing, and they still did not quite want to answer. Right? So cloud computing is anything that has some sort of internet access one way or another to allow some sort of two machines do the same thing at the same time, maybe, because they call cloud computing even things that didn't have this characteristic. Right? So cloud computing is one of the biggest buzzwords. Literally, they took everything that happened in distributed systems for the last 40 years, and they said, let's call this cloud computing because it's going to sound so cool to the normal people. Oh, it's in the cloud now, right? It's whatever it is, it's in the cloud, right? And then Amazon Web Services goes down and takes down 100 important websites because everybody was in the cloud, right? So distributed systems are their best, I guess. Okay. Now, grid computing, it's another big buzzword, but more in the scientific world. They said, hey, we want to generalize a little bit the simple model in which you have a master and you have computer nodes and so on. Let's put together millions of machines, right? All the universities have lots of computers. I mean, we have lots of computers at UF. We have lots of computers at other universities. Let's just form this kind of computational network between them. So ideal situation would be, I need to run a large-scale simulation, let's say. All right? It's very easy to do large-scale simulations. All you have to do is to say, hey, let's simulate, for example, how 100 billion stars gravitationally interact with each other to figure out if the shape we see for galaxies makes sense or not. You write some differential equations and just solve them for 100 billion points, right? So it's easy to describe, but takes forever to get anything done in that area. So then the idea was, hey, we need some sort of a protocol, some sort of communication between all the parts involved so that we can even schedule such jobs. Then we have many problems, right? Machines are far away, so large latency. So we cannot really communicate very fast and cannot make that assumption. Machines go up and down. What happens then, and so on and so forth. And they started designing these kind of protocols for grid computing. The trouble is they never finished, and they never really got to a point where they have a standard that everybody uses and these kind of deployments go, because people said, hey, it's not cool enough, let's go and do cloud computing, right? Which essentially is what grid computing was trying to do in the first place, but with slightly different variations on top of it. I'm not going to go through what it takes to do it, right? Because it's not even clear that this is the right solution. Let me tell you also a kind of a secret. Nobody really knows what the right solution is. You have solutions, you have things. But so students ask me quite often is, I want to do this, what's the best solution? Well, my answer always is, I do not know, because it depends on so many things. You can turn on and off some of those obsessions, right? Or some of those pitfalls that you care and you don't care about. And then you might find a solution for those circumstances. But the trouble is, which ones should you keep on and which ones should you keep off? To a large extent, until you build it and you deploy it, you don't quite know how it's going to work, right? And a lot of the things that look good when you've done only a simulation of how they might work were, in fact, disastrous when you deploy them, right? And things that theoretically should not have happened, happened nevertheless, right? Google going down 3 minutes, Amazon Web Services going down for almost a day, right? Now, transaction processing systems, how many people know what a transaction is? So what are these transactions, right? I mean, first of all, why should we care about? Why do we invent so many complicated topics and so many complicated gizmos and then spend a lifetime trying to do something with them? Why should we care about transactions? I briefly mentioned this before, right? Transactions are important because they simplify the way the user can think about what's going on. I'm sorry?
Transfer system from consistent state to another consistent state.
No, that's not what transactions are all about. What transactions are really all about, okay, is to make a very strong promise as a system to simplify what the user thinks is happening. So it allows you to wipe out mistakes by just saying abort transaction. All right? So think about it even for a program. You can say begin transaction, go and change variables and do things and so on, and say, hey, I ran in trouble. Why don't we forget that I started whatever I wanted to do, abort transaction, and make it exactly like it was before? Wouldn't that be cool? Right? Say, I ran in trouble. Go back to the point we had 5 minutes ago, and let's start from there because I'm going to try to do things in a different way. That, as a user, right, that's one way. Or the counterpart, which is you start doing something, you do whatever you do, there is always a possibility you have to cancel. But when you know for sure that you completed the task, you say, hey, I want to now to remember this state. And in particular, I want to make sure that if I make modifications to that state, and somebody else makes modification to the state, to me it looks like a simple scenario in which I was the only one modifying the state. So these transactional systems allow you to have this significantly simplified view. I'm the only one using the system. I can roll back. That's kind of the aborting transactions. Or if I say, yes, the transaction is committed, then everybody knows transaction is committed. Right? This is important, for example, when you do money transactions. Right? You can get in sophisticated scenarios in which you want to basically go, move, for example, move money between banks. You have to take money from one and put it in the other. So it has to be the case. It doesn't matter if there are glitches, if people plug the cord or whatever they do. It has to be the case that you either didn't do anything in the first place and you tell the user your transaction got aborted, or you tell the user your transaction made it through and then you took the money from this bank and you put it in the other one because otherwise you're in trouble. You have to conserve the amount of money because otherwise it's not good, right? So these transactions come from database systems, were first implemented in the super expensive database engines, right? But now we are interested in this kind of distributed transactions across database transactions, in which I might have an airline database and some bank database and whatnot, and I want, if the transaction, the overall transaction goes through, and I think there is a picture here. Yes? Right? These are nested transactions, right? If the transaction in the airline database goes through, the hotel database goes through, then the whole transaction goes through, but if there is any failure anywhere, you have to roll back both, right? Now, from the user's point of view, it's fantastic. From the application design point of view, it's fantastic. You just say begin transaction, do whatever, end transaction or abort transaction. No worries in the world. From the system point of view, it's really, really hard to implement these transactions. So what we are going to be interested in this class is how do you implement these distributed transactions when multiple parties are involved. You see, the trouble is, it's not enough to have one server say commit and another server to say abort. That's a disaster. So imagine that you have 100 servers involved. We're going to see these examples in class. 100 servers involved. They all keep copies of the data. You have to replicate data to keep it in all those different corners of the world to run faster, right? And they all now have to agree whether they commit or abort. Oops, right? So it can get very, very tricky. And even if you have multiple servers in a single rack, it can get tricky because your expectations go higher. I want to run 100,000 transactions per second, right? And then a message looks too slow, potentially. And none of these things have unique solutions or perfect solutions. It's almost always about a compromise that's acceptable for those kind of circumstances. And it's all about compromises in computer science, by the way, right? Can we find a reasonable common ground between the requirements and what's possible to do? Now, we know for sure that is not possible theoretically to produce ideal solutions for certain problems, and those are what the negative results are all about. A negative result in distributed systems essentially say you can't have your cake and eat it too under even relaxed circumstances. I mean, we're going to make that precise later what it means. Okay? Or you can have your cake, eat it too, but you need something that you can't have, like a global clock. Right? So something somewhere has to give. You can't really have everything. Now, that doesn't mean that you cannot have practical solutions. It just means that if you have unrealistic expectations, you can't achieve them. Any negative results from math I should know about? Right? This is what Gödel did, right? It cut down deep into the heart of the mathematicians by saying you cannot axiomatize arithmetic. That was devastating for mathematics until they figure out that it's a profitable business to prove more negative results. Anyway, so yes. Right, this is how a transaction processing system might look like, maybe. Some sort of a monitor, the client talks to the monitor, and the monitor talks to multiple servers. Extensive discussions in class about it, right? Enterprise application integration, this is a very, very big area. I mean, UF, it's in fact an enterprise. We have hundreds of thousands of computers, very sophisticated database servers that don't always do the right thing, right? How do you make all of those things come together and have some sort of a smooth information sharing, right? This PeopleSoft system, right? It took only 10 years to make it not be really bad, all right? Now, pervasive systems are really these cell phones that are everywhere or other devices, right? Google Glasses, right? Who doesn't want Google Glasses? Right? My kid already started saving money for Google Glasses. He's 11. That's the last thing I want in my house, right? Google Glasses. But so these systems are, so because now we can put electronics everywhere, you can have, hey, smart watches. By the way, apparently Samsung is going to beat the Apple with who's going to produce the first smartwatch. They announced some release date in September. Okay, so start saving money. There is already a startup that it's trying to do the same thing, so on and so forth. Right? So these devices are basically everywhere, or they're talking about medical systems in which you put all kinds of sensors and all kinds of tags on everybody, and then you know how everybody is doing or not doing. So it's what they do with the astronauts when they go, at least they used to. I'm not sure if they still bother now, right? When they send people on the moon, they had these sensors on them so that the doctors on Earth could monitor them and know what's going on with them. You have no reason not to do that from a technological point of view in the next few years. But the question is, what are you going to do with all that information? How do you put it together? How do you process it? How do you not overwhelm the systems? Systems are already very overwhelmed even with much less information, right? Cell towers are overwhelmed even by this relatively simple communication you have with cell phones, right? So you could have these things everywhere. You can technologically pull them off, but then you have to do something with it. They're talking about putting sensors in the cell phone. If you would have a temperature sensor and a pressure sensor in the cell phone, you don't, I mean, you could do a very different kind of weather prediction. You simply have on-the-ground measurements, right, in millions of points with extremely high accuracy. You don't have to say the temperature in Gainesville is whatever, 78. You have a detailed map of what the temperature in Gainesville is. Now, that's the good news. The bad news is, how do you put all that information together? How do you get it out of the system? How do you push it in the computational model? Could you really do better in the computational model, right? So you're first happy that you get more data, and this is the data gold rush, but then you get very upset that you have no particularly good means to mine the data. This happened, for example, with the Genome Project. Billions of dollars invested in sequencing. But then you say, OK, we have all of these genomes now. Now what? Right? Where is that cool stuff we can do with the genome? Well, we do a little bit, but it's like, right? Well, lots of other gold rushes, right? For example, the particle accelerator at CERN, right? It's measuring all of these things, but in the end, it just says, oh, yes, so there is this particle or there's no particle, right? So from trillions of measurements, you just get, oh, yes, we found Higgs. Okay? It's there. It only took 4 months to compute whatever they were computing from that, right? So extracting knowledge from such vast amount of information is still not necessarily a figured out issue. But of course, you first have to gather the data. I'll talk more about that, okay? So that's essentially my overall introduction. There are more slides here. You can look at them. Health systems, sensor networks. I'll talk more about this later. This is the kind of stuff we want to solve in terms of problems. The question is how. And that's what the rest of the class is going to be about. And you're going to have lots of projects to solve them yourself in Scala. So start perfecting your Scala skills. I'm going to throw the first project in. And you're already going to accomplish some interesting thing. I'm going to ask you to find a specific kind of numbers. And this is an interesting problem that popped up in a math paper, right? The math paper proved that only certain numbers have a certain property. You're just going to find all of them because that's the nicest way to check a theory, right? You just go and brute force compute. OK? All right, so I'll see you Tuesday. But in the meantime, I'll post. Oh, no quiz this week because this is fluff stuff. So once I start teaching something real, we'll do a quiz next week. Or this week, start learning Scala.